today is the last class on the cut matching game. Yeah. So today plan is to look into two extension of cut matching game. On Friday, we look at the one with deletion, with like there is an active set, and the matching player can choose to delete some set of vertices. And today we're gonna look at the version where the matching player can transfer vectors. We'll see what it means here. Yeah.
Just one question. So I was scribing on Friday. Should I continue scribing today?
No, like you just do the one for deletion.
Okay.
Yeah. So I updated the lecture note from the previous one. Like I split this thing out, so you can look at the updated lecture note and just scribe only that. Yeah.
Okay.
Yeah. Okay. Also, like I kind of quickly go through how to deal with arbitrary node weighting, like on last Thursday, but like that was a bit too quick. I just gonna do it carefully today. Yeah. So you didn't need to scribe this one too. Yeah. Okay. So okay. And then we're gonna look at the state of the art of what's known for the cut matching game, and there are many open problems. Okay. So yeah, like this version is not really taught anywhere, I think, and it's been presented in some paper that is really hard to understand, but we're gonna learn it today. And with this, it really gonna give you like the state of the art technique that lead you to the fastest algorithm. That's why I teach you this. Like, yeah. Let's see. Okay. And yeah, because today is just gonna be the last class on cut matching game. After this, on Thursday, we're gonna just now like start to use it. Right? We spend several classes for now to just study cut matching game. It's quite natural. It's like you try to build like a graph that is expander under adversarial matching. That is not too clear why this is like why we want to use it, why we want to study it. It's going to be more clear from next class. Okay. Okay. But today, still gonna be on the cut matching game. And let's recall the game with deletion. Okay, let's recap this, right? This is a game where there are like, the game works as follow. Yeah. You start with empty graph with n vertices, right? And then you initialize the active set of vertices to be everything. T0 is all vertices, and they start to be active, right? And then in each round, what will happen is that the cut player will look at, this is a graph G. The cut player will look at the current active set, right? And the cut player will choose two sets, AI and BI, between the active set, right? That's what will happen. Yeah, the cut player choose this thing. And let's assume that AI is smaller than BI, but doesn't really matter. And in normal cut matching game, the standard one, right? The matching player will just match every node in A to some node in B. There gonna be maybe some node in B is not matched, but everyone in A is matched. That's what the matching player will do in the standard one. For the one with deletion, the matching player will choose some set of A to delete, and the rest will be matched. So you delete something, the I here, right? And then once you delete the I, then the active set, this should be active from previous round. And once you get this, you set T to be delete. You delete this deleting set, and yeah, you add a matching between the part that you don't delete to BI. Okay, and then you add your matching. Then the graph is updated by just adding the new matching to the graph. Okay, that's what we learned on Friday. So can you recall what is the guarantee that we say about this game? Like after log square round, what happened?
So I think if you can find the matching every time, there is still an expander.
Say again, what is expander?
So there is still an expander on the sets you remain at last.
Say again, sorry.
I think TI still from an expander.
TI is expanding. Yeah, exactly. So we said that at the end, after log square round, we guarantee that TI, like the indicator of TI, is basically expanding in which graph?
GI.
GI. When I is like something like log square. That's what we showed, right? So in the standard version, TI is just like without deletion, TI is everything. So we get that this is like an indicator of the whole vertex set. But here you might delete something, and we just said that the part that is still active is going to be expanding at the end. Okay. Do you recall how did we like what's the strategy to prove this? We look at some potential function. Was that? How like the strategy to prove this thing? How did we do it?
I only remember it's like how close the probability distribution is to to the same one for every node.
Yeah. So yeah, exactly. We look at kind of, let's say that we look at, we said that this is like a probability distribution of a node A, right? And we look at how close this thing is to what? Yep.
The average or mean position at TI? Or?
Yeah, the average of TI. So let's say this is like mu of TI. So what is mu? Mu of TI is just really the sum of the position of A, summing over the guy in TI, and average them. Right, this is the average. So we look at this thing, how close this is to the average, and and then we look at like the size of this, the norm here, right? And we look at the total distance of everything here to the average. So that's the potential. Exactly. Yeah. So that's what I'm gonna ask. There is something missing, which is a square. Okay. So we use the square norm. And do you kind of recall why did we use squared here?
It's because we later take like a random vector and project the positions, and square distances are well preserved.
Exactly. Yeah. It's like when we use random projection, the thing that is preserved under random projection is square distance. Yeah. So that's like why it's convenient to work with this potential, right? Okay. And what did we say about this once? What did we prove about this? Yep.
If it's less than 1/4n squared, then so basically like it doesn't have to be zero, exactly zero. It can be like very low, and then we can still be kind of flow expanding.
Good. Yeah. If this thing is tiny, but not too tiny, just like polynomially small, 4n squared that works, but like that works for the standard version. For the deletion version, we kind of make it a bit stricter to 16, but doesn't really matter. Then we conclude that we show that this thing is basically something like flow expanding in GI. This is what we showed. Okay, good. Again, can you recall what exactly is PI? How is PI defined again? Just want to remind. Okay. Yeah.
Like we have a matrix of transitions of like probability mass from each matching. So it's the edges and the matching that allow mass to flow from the previous positions.
Right. So PI kind of keep track of the probability mass of everyone when you look at the round robin walk process, right? So this is like P of UV is just how much the probability mass starting from U and at V after I step of round robin walk. Okay, good. Okay, good. So that's just to recap what we have learned. Okay. And how to prove this, if you don't recall, you can look it up. And okay. Yeah, so this is what we showed. We showed that, the card player can choose, there is a strategy that the card player can choose AI and BI, right? In time, something like NI, such that AI is small, BI is more than half, and after log square round, then TI is expanding in GI. Okay, and we prove this by look at this potential function, right? Once this is small, then this is expanding. Okay, so now that's what we learned about the game with deletion. Okay, and now I'm just gonna start talking about the transfer vector operation. Okay, so imagine this. Imagine that I have the active set Ti so far, like here. Okay. And then I add, let's say that I look at this matching M prime, where one side of M prime is inside Ti, another side is outside. Okay, so I match active guys to inactive guys. Okay, so the part that is matched and is active, I call it S from, and this is another side is S2. We match S from to S2. S from is in TI, S2 is not. Okay. So then I just gonna imagine that what I'm gonna do is to kind of update my active set just by saying that I kind of move the active part from the FS from to S2. Okay, so like this thing become inactive, and this and S2 become active. So this is how you can imagine what is the new active set. Okay. And then you imagine that you just really kind of transfer the vector from each of this guy to this guy. Okay. So the new position, the new matrix Pi now is Pi prime. Okay. Is as follows. Like for each matching from A to X, okay, what we do is just transfer the vector at A to X. So what happened is just like Pi prime of A, the position of A is now just empty, just zero vector. And I just move it to the one at X. Okay, I really just like move the vector of A to X. Okay, good. And then the one that is not, the one that is like not in the matching, well, it's just stay the same. Okay. So this is just what happened. Just transfer everyone in S from to S2. Okay. Okay, so, and here is the claim. I claim that this Pi prime, when you look at it as the demand, right? Pi prime is a matrix, and you can think of it as the demand. This Pi prime is routable in GI union the matching with congestion 1. Okay, so why is that the case? Okay, so first of all, we know that Pi itself, with like Pi before you transfer the vectors, we learned before that Pi is routable in GI with congestion 1. You remember this? Like it's just how we, like, this is the property of this Pi. Yeah. This thing is routable in GI. Okay. But now what we want is to say that Pi prime is also routable. Maybe not in GI, but when you add this matching, M prime, then it's also routable with congestion 1. Does anyone see why this should be true? Okay.
Could we set the mass of the old nodes to 0 so we can just route all of the mass of the new nodes to the old nodes along the edges in M prime, and then our existing routing should work?
Exactly. So what happened, right? I mean, we just like, suppose this is A, this is X, right? What we really need to do is like to make sure that now whatever mass distribution at A should now be at X. The total mass distribution, the total unit of mass at A, this is of size 1, right? It's a distribution. And it should be now at x, so we can really just literally send this, like this 1 unit of mass through a matching edge, and it now ends at x. Okay. So, and like this has capacity 1, and you send 1 unit of flow along this edge. So the congestion on GI was 1 to route PI, and now on top of that you route through M prime. That has congestion 1 too. Okay. So is everyone convinced that PI prime is routable in this graph with congestion 1? Okay. Okay. And the next observation is that the potential function does not change at all. In what sense? I mean this. I mean that if you look at the potential function with respect to Ti, which is just the sum of like the total square distance from everyone in Ti to the average, it's just the same as the potential function with respect to Ti prime. So why is that? Like this, nothing happened here. It's really just renaming, right? Like the thing that used to be in this sum is we are summing the same thing. Like the thing that used to be in S from is now moved to S2. And now it's just a summing the same thing, but we changed the name. Okay. So it's just the same potential. It doesn't increase, it doesn't decrease. It's just the same, okay, after this operation. Okay. Good. So what do we learn from here? We learn that the point is that I have ability to move anything from the active part to the inactive part as long as I add some matching. Okay. Whenever I add a matching M prime from the active part to the inactive part to the graph, then we can literally just transfer the vector from S from to S2 through this matching M prime. Okay. And we can update the active set to be Ti prime and update the position to be Pi prime. Update active set and position. Okay, without changing potential. So you should think like, whenever I want to move the active part to the inactive part, I can do it for free. It's like at any point of time, as long as I add this matching from S from to S2, I can just do that. And then the potential doesn't change at all. Okay. And so you can imagine that when you run the cut matching game in every round, right? If at some point you want to move things, you can just do that as long as you add a matching. Okay. So now I can define the game when you have both deletion and you can transfer the vectors. Okay. Yeah. So this is a version where it's going to be useful for when you find expanding balance separator. Okay. Okay. So imagine this. Okay. Yeah. In route I, right? It used to be that in route I, the matching we have AI and BI. The matching player used to just delete something, and then match the rest. That's what happened before. And so instead of doing just this, what I'm gonna do now is just imagine that we're gonna move something first and then match. So imagine that we just add this thing that we call transferring matching, mi prime, like which gonna move something in ai from to a2. Yeah. So this ai from to ai2. Okay. So like I choose the part that is active, ai from, and the part is not active, ai2. This is kind of, this operation you can think like I just gonna transfer everything here to the AI, from to AI2. At this point, nothing changed at all. Literally I just add this meshing and transfer whatever is there in AI from to AI2. The potential function stay the same. And now, what happened next is we just added like standard meshing that we have been doing so far, the meshing for mixing probability. Okay, so we're just gonna now add a meshing between this part and this part to B. Okay, so it's AI when you remove the deletion thing, the deletion part and the from part, and you add the two parts. So it's this. So this thing is this thing. Okay. So you just match everyone here to BI, and then just update the vectors like before. Okay, that is everyone for each of the guy in this meshing. If this is like P, if this is like at position, if this is B and the position of it is B, after this meshing, then the position of these two vectors are just average. Yeah. Okay. So just imagine that in each round, instead of you used to have that the matching player delete some part and match the rest. Now it deletes some part, move some part, and match. Okay. And this is just a summarize of what you can say, but it's really just what I just said. Like it's just the same thing where like you start with empty graph. In each round, the cut player choose an active set like AI and BI, and then the matching player deletes something, transfer something from the active part to inactive part, and then match the blue part here to BI. Match the blue part to BI. And then we just how the active set is updated. It's just like what you expect, right? You delete the thing that you delete, and kind of transfer the from to the AI from to AI2. Okay. And now, importantly, how you update the graph, you add the matching, the mixing matching, and also you need to add this transferring matching so that it's valid to transfer vectors. Okay. But so you see, as long as you believe that with transferring vector, with transferring matching here, it allows you to just move vectors for free without changing potential. Then you should be convinced that if you run this game for log square round, this thing will happen. The potential will be small. And the active set is going to be expanding. Now the active set is not the decremental set. It doesn't only undergoes deletion. The active set change through round. It move in each round, but it's still going to be expanding. Question about this? Yeah.
I guess we may cover this, but like, when would the matching player like want to delete versus transfer? Like, what's the incentive?
What's the motivation? Why we would want to do that? Like right now, it's not too clear. Yeah, I totally see this, and we will see why we want to do this. Like when we try to build fast algorithm. Yeah. So when we try to build fast expanded decomposition, you see that you want to delete something. And once we want to build fast algorithm for expanding balance separator, you're going to see that we want to move something too. Yeah. So this will become apparent when you see fast algorithms. Okay. All right, so this is like the theorem that we're gonna just refer to later in class. Okay, when we want to build fast expanding separator, even when the matching player can delete vertices and transfer vectors, well, the same thing happen. Yeah. So you can the cut player can choose something quickly, and after log square rounds, the active set is expanding. Okay. Okay, good. Any question about this? Good. So next, I'm gonna look at the game for arbitrary node weighting. Okay. Just kind of to repeat, but slowly. Yeah. Okay, so maybe let's consider the standard card matching game again. When there is no deletion, no transferring vector, right? We showed before that at the end of the game, then we know that the all one vector is expanding in the graph. And the question is, what about if we don't use all one vector? What if we replace all one vector with some node weighting? And I'm gonna use this notation instead of A. Let me use D. Okay. This is a node weighting. Okay. I don't use A just because it will be confusing with AI. Okay, so let's see how to do this, right? For the standard card matching game, but all the discussion below will just generalize to the game with deletion and transferring vectors. But yeah, you can just imagine how. Okay. So the first thing is like you can imagine the symbol reduction. Okay. Just simple reduction to standard card matching game, where let's say that D is actually not a real but integral. It's integer. Okay. Then imagine that for every node V, just make dV many copies of vertices. Right. So if D is like 3, 2, and and 1. Then we just make this kind of cluster of vertices like this, right? And now I'm gonna call this thing V prime. So the size of V prime is just exactly the size of D. Okay. And then just run the cut matching game on this graph G prime 0, where this is start with empty graph. Okay, if we run cut matching game on this G prime 0, then we know that at the end, we're gonna get that IV prime is expanding in G prime last, G prime I last at the last round. Okay, so we're gonna get like that after adding some matching. Yeah, this is G I last, G prime I last, and IV prime is expanding in this thing. Okay. And okay, once we have that, we can just say, okay, imagine that you just now contract. Let GI last to be just GI prime last, G prime I last, where we just contract the cluster of vertices back. The copies of V is now contracted to one node. The copy of this guy is now contracted to one node, and so on. Okay. So the key observation is that now D should be expanding in I last, GI last. Okay. Anyone has some reasoning, like why do you think this is true?
Can I just say if you have flow expanding thing, then like sending from any copy to any copy is basically the same as sending the same nodes.
Yes, good, exactly. So the way, yeah, so maybe I should say that if this is like a phi flow expanding, then this is gonna be phi flow expanding too. And the way to think about this is just the following. Like, imagine that you have demand that respect this node weighting, and you can send this with congestion 1/phi, because it's phi flow expanding, right? You can send the demand on this graph before contraction. And if you just look at the graph after contraction, the congestion cannot increase, right? So maybe I should say this. Consider like let E prime be this thing respecting demand. Okay. Then we know that what we know, D prime is routable in G prime I last. Let me just write GI, yeah, with I last, with congestion 1/phi. If this is like phi flow expanding, okay. And maybe I should start with this. Like, maybe I start by like let's move this a bit here. Maybe let D be D respecting demand in G I last, right? When you look at the D respecting demand, now you can just like kind of define D prime, the corresponding D prime. That is one V prime respecting demand, right? For example, if I want to send two units of flow from this supernode to this supernode, I can just define like now that I want to send 1 unit of flow from this node to this node, and 1 unit of flow from this node to this node. Okay. So like, you see what I mean? Like how to define, how given D, you can define like a corresponding D prime. Okay. That is like that is 1 V prime respecting. And this is routable with congestion 1/5 in GI prime last, GI last prime. Yeah. But now, like, so look at, and like it's routable by some flow f prime. Okay. But now imagine that you contract the graph to get GI last. Now, after contraction, congestion doesn't increase. And after contraction, the flow f prime here will now route D with the same congestion. So it just means that then D is routable in GI last too. GI last with congestion 1/5 as well. So anything that D respecting is routable with congestion 1/5. Yeah. Yeah.
So just to clarify, when you contract, you're combining all the edges into one like super edge, right?
Yeah. I really just make this one to be one node.
Right. So if you had like two A's and two B's that are now A and B, they had two edges.
Oh, so you say that it's a parallel edges.
Right.
Yeah.
So you still have the same edge capacities and the same flow.
Yeah. Yeah. Exactly. Yeah. Right. So if you have two edges here, after contraction, you can think like you have two parallel edges. The flow that goes through this guy is the same amount. So the congestion don't increase. It kind of just literally just said that everything outside the contraction stay the same. Everything inside the contraction here, you now forget about the congestion inside the part. So, okay. So this is expanding. So that's it. Like, just work. This is just how you reduce the problem to standard cut machine game. And now at the end, you get that D is expanding, not just like all one vector. Okay. And what does this give us? It means that given any node weighting D, right, there is a way for the card player to choose AI and BI in this time, D times I. Why D? Because it runs on this G prime. The size of G prime is D, right? The number of nodes in G prime, the number of vertices of G prime is D. So that's why the running time is this. And then after like log square of number of nodes in G prime rounds, then D become expanding. Okay. So that's it. Like you can make it work like this. Okay. However, Any question up to this point? Yeah.
You said before that the node weighting D is only like integral node weighting. Would it be possible to somehow generalize to some real numbers or?
Yeah. So with this reduction, it just works for integral one. If it's not integral, you can imagine this too. Let's say that it's the multiple of, like, let's say 1/k. So it's not quite real number, but like, let's say 1/2. Yeah. Yeah, we can make it 1/k. Then what we can do is like, we're gonna make, instead of dv copies, we're gonna make k dv copies. Just so that everything become integral again. And then you scale it down. And so the more fractional it is, let's say this is like 1/k here, then the total running, and you make these k copies, then the size of v now is just gonna be k times the size of d. So like, the more fractional it is, the less efficient this reduction is. Okay? So not so great. Yeah. So that's it works, and it works in some application, but maybe you don't like it. So that's why, like, okay. So this above reduction that we just saw can be too slow when d is too big, or when d is really fractional. Okay. But the idea is that you can still make it fast. And it kind of motivates the definition of cut matching game that kind of directly work with any node weighting, not just all one vector. Okay. And the version that makes sense just gonna be like this, where you define B meshing. Like, this is a standard name in the literature. B meshing is just a graph such that given any node weighting B meshing M is just a graph where the degree respect B. Okay. So all one meshing is just a meshing. Okay. And the game of the cut matching game, the natural generalization just gonna be like this, where you start by, you have a graph, and then you choose this choice set A and B, such that the size of A is smaller than the size of B in terms of the node weighting D. Okay. And in each round, the matching player, instead of choose the matching, they choose D matching. Okay. That match A and B. And the size of the matching, like here you kind of, you have A and B. And now like you choose some matching, it's gonna still be bipartite, but if this is 2, this is 2, then you just choose M to be like this, like 2, like even if it's fractional, it just looks like this maybe. Let's say it's fractional. Let's say this is like 0.7, this is 2, this is 1. Then it can be like, M can look like 0.5 here, 0.5 here, and 1 and 1 here, and then 0.7 like this. Okay. So just make it such that you, like the degree here, just match A completely. Okay. And then you just add this matching into the game, into the graph. Okay. And this is just gonna work. Like, now why I will not prove it. But what is true is the following. So suppose that, so now you see that like I allow fractional thing. And if I allow fractional thing and I allow like each edge of M to be fractional too, then the number of edges in M could be anything, could be really huge, right? So now like suppose that I set up all the meshing from the meshing player in this game above has at most M edges. These edges can be capacitated, right? Like here, it can have fractional value. But like if it has only M edges, then we can say this that the cut player can choose AI and BI in this time. So it can choose it in time M times I. You can spend at most D as well if D is small. Like if you're gonna spend this time, then you can just use the previous approach, but you can spend M time here instead. Okay. Actually, maybe I shouldn't use this thing at all because here I can pay this only when D is integral. So maybe let's say just M. Yeah. Okay. And after log square round, so note that this is now not D here. This is like just N. Even D is much bigger than N, we're just still gonna pay N. Okay. Okay. So this works, and how to do this? Well, the idea is kind of to simulate the reduction, but do it in the analysis. Just kind of follow the same approach, but just do it in an analysis, and then it works. Okay. It's not so like illuminating to do this here, but okay. By the way, this is not really proof explicitly anywhere. And here is really approachable project if someone wants something quick for the project. So this paper by Jason Lee, Satish Rao, and Di Wang, they actually proved this theorem when I last the number of rounds is something like log square times D, log square of N times D. And this can be quite big if you think of D as something huge. That doesn't really depend on N. But we can make it just log square N actually. So like with some simple trick, we can reduce it to just log square. Okay. How exactly we can chat about it, but if you want to kind of write this thing up, you can. Yeah. You can like think how to make this work. How to make this work? Like so, if anyone interested in this project, it's like you're gonna see how to prove this formally with this factor, and then we can discuss how to improve this factor to just log square N. Okay, that's okay. But the point that I want you to get from this discussion is just that whatever we learn about cut matching game for all one vector, we can make it work for any node weighting without any concern. Yeah, it's gonna be still fast and you don't lose anything. Okay. Any question about this? Okay. So now let's recap what we have learned so far. about card matching game. Like you have just learned like really the state of the art card matching game. Like, yeah, it's really kind of at the frontier here. Okay. So we have learned 3 versions: the standard version of the card matching game, the one with deletion, and the one with where you transfer the vectors. Okay. This is good for approx sparse cut. This is good for expander, decom position, and this is good for expanding, balance, separator, balance, separator. Okay. Also, we learn how to work with a pre-node weighting. Okay. But here is the state of the art. Let's focus on like even the standard version. Okay. For just all one vector, here's the state of the art. This version that we learned is from this paper called KRV, Kadeka Rao Vasirani. Okay. This we learned. The number of rounds is log square, and we conclude at the end that all one vector is flow expanding. Okay. It's one constant flow expanding. The running time is n log to the 4th. It's randomized. But actually, in this paper, it improved upon KRV. In what sense? This is like Orexia, Shakdewa, Vishnoi Vasirani. It basically has the same thing, but it concludes log n cut expanding. Okay. So log n cut expanding doesn't imply, it implies O1 flow expanding. Right? You remember like cut expanding and flow expanding are almost the same, but cut expanding is a bit weaker. But it's weaker only up to log n factor. So like cut expanding doesn't imply log n flow expanding. Like log n cut expanding doesn't imply log n flow expanding, but it does imply O1 flow expanding. So this thing implies this. Running time is a bit slower. Yeah. But this is again randomized. There is this one that I will guide you in the homework. Yeah.
Just about the first two, like doesn't omega 1 flow expanding also imply the second one?
No, because this is more than one. Like, so this thing, I mean, so phi flow expanding implies phi cut, and phi cut implies flow. So this only implies like O1 cut expanding. So note that this is more than one, right? And it's possible because like the degree of the graph is more than one. Yeah, make sense? Yeah. Okay. So this is randomized, and there is a version that can get deterministic. It's by Keiko Ovi. I'm gonna guide you how to get this in the homework. Okay. And the number of rounds is just log n. You get O1 cut expanding, weaker than both of this. And but the running time is exponential. You can make it a bit faster, like polynomial, but still big polynomial. And it's even worse. It's now 1 over log, square root log. But this is deterministic, so it's quite nice. Like something like during my postdoc, together with Julia Chusoi, Yu Gao, Jason Lee, Danupon Nongkai, Richard Peng. We show that we can get deterministic version too, and it's also quite fast. It's almost linear time. But like this expansion is quite bad, but still good enough for application. Yeah. So as long as the expansion is not, it's like kind of close to constant. This is like kind of 1 over into little 1. So it's kind of something like, it's not polynomially bad. It's like close to constant still. So this is still good. But what's open, and it's like one of my favorite open problem. If you can do it, like, I give you PhD. Like, I really like this problem. So can we do it deterministic and fast, as in like really just n polylog time? And this is like 1 over polylog cut expansion and polylog rounds. So like kind of remove n to little 1 to polylog. That's really open. Why this is good? Because, you know, like once this is solved, then there are like tons of deterministic algorithm in graph algorithm right now got stuck at this time. Why? Because it's based on this thing. If you get this, then the whole host of problems will be improved to this. So like it's just a key bottleneck in this area. Okay. Yeah. And you see soon that if you have cut matching game, then you can approximate the expansion. So approximating expansion in some sense is kind of easier than cut matching game, because if you have it, you can approximate expansion fast. You'll see this on Thursday. But it means that the bottleneck is just how can you approximate expansion fast, deterministically? So like, can we get a deterministic algorithm for distinguish these two cases? Let's say the first case is when the graph is really good expander. And in the second case, when there is really bad sparse cut, but like just 1 over log square, 1 over polylog. If this is like 1 over n to the epsilon, then we already have something like, what we know right now is, if this is n to the epsilon, then there is an algorithm with this kind of running time, log to the order of 1 over epsilon n. But I want this to be just like polylog m times polylog, and this is just polylog. So that would be great. Okay. Let me mention some lower bound. So you might wonder, like, how many rounds do we need? Like, all these things need some number of like log n log square rounds. Can we reduce the number of rounds? Like OSVV, this paper, OSVV, it shows that if you want the all1 vector to be expanding, then you need at least square root log rounds. So it's not tight yet. Okay, we know how to get it with like log square round, but the lower bound is square root log. There is another paper by Sherman, which talks about something else. I didn't talk about, like, this is about spectral expansion. I don't have time to talk about this, but if you are interested, you can have a look. Like, they said that, like, under some notion of expansion that is related to eigenvalue of the graph, then you need log n. So it's kind of improve upon this thing. But I cannot talk about this right now. What this thing is. Like there's like a second eigenvalue of Laplacian of the graph, but can have a look if you are interested. This is like second eigenvalue of Laplacian of G I last. This is just a keyword. If you wanna Google or look at ChatGPT what this thing is, then just search for it. Okay. But the point is that some lower bound is known, but we don't have like a clear understanding what's the best. Okay. So that's like some interesting open problem that like gonna list below that that maybe you can work on this thing. Okay. By the way, like there are card matching games for several related notions of expansion. Later in class, we will talk about directed graph. We have been talking only about undirected graph so far. There are directed graph, and we can talk about directed expander. I will define it later in class. But I just want to mention today that like there are several card matching game that is adapted for directed graph. Later in class, I might just say that there exists this card matching game for directed graph without proving. But if you wanna see how whether it works or not, it does works. It does work, and people prove it. Yeah, and there are something called length constant expander, bipartiteness, and so on. Can have a look if you are interested. Anyway, here is some open problem that I want to ask. Okay, so basically, I think given that you kind of have learned the state of the art of card matching game, we can ask about like you can try to understand the trade-off between the expansion and number of rounds. Okay. So for example, can we hope for constant round? If not, then like this thing says that if you want this expansion, you need like a square root log round, so not constant. You need more than constant. But what is the best you can do with constant round? Say, that's the question. Okay. And there are applications that we will see more. But so suppose that I give you just k round. Okay. What's the best expansion that you can get? That is the question. Can you still get it to be like 1/polylog expanding instead of constant expanding? Or what if we allowed adding many matching, not just one matching, in each round? Okay, that is also another approach. Like, okay, maybe you can prove that with k round you cannot get good expander for sure because it's just a constant. But what if I allow the matching player to what if I say that the cut player gonna choose AIBI, CIDI, EIFI, and the matching player need to add matching for each pair of sets that we choose. So the cut player have more power, right? It kind of force matching player to add matching in many places. If I allow let's say if I allow a cut player to choose k pairs of set, n pairs of set, then you don't need to do anything. Like I just say that cut player choose this pair, just one pair here, another pair, and it really just force the matching player to n pairs of things, so I can construct the whole graph in one round. But what if I say now I don't choose linearly many number of pairs, but something still quite small. I suspect that this number is the correct one. Then can you still say that it works? Yeah. Okay. So if you allow this many different matching per round, then this paper proved it already that it works. But it's slow again. It's like exponential time. Can we make it fast? That's like, can we kind of get some randomized strategy like what we learned and make this thing fast? That's a good question. Okay. Yeah, second question is just kind of what I kind of asked. What if we just want it to be 1 over polylog expanding instead of constant expanding? Does the lower bound apply? Can we say that we can improve it to square root log rounds or even constant round? This is a good question. So to understand this, it's just it will require you to kind of read the lower bound paper and see if you can extend the lower bound or like how weak, how strong this lower bound is. Yeah.
If it's constant rounds, can the graph even be connected?
Good. Let's see. Good point. Good point. So if it's you need log n rounds. You're right. Because it could be the case that. Wait. Sorry. Maybe like in the beginning, you might have like you have matching. There are like n over two components. In the second round, maybe like in the worst case, you might get like another matching that just reduce the number of components by half, I think. Can that happen?
But you can choose what source to. Okay.
Right. But I just imagine that if I have, like, if my current graph is just a bunch of matching like this, then the only cut that makes sense is just to choose this thing and this thing. And then like a matching player can just reduce the number of my component by half. So it seems like log n rounds is needed just to make it the graph connected. But yeah. So yeah, maybe the question is then, can you reduce the number of rounds from log squared to log n? Or if you have less than log n rounds, maybe you might need to ask for more matching, not just one matching. Okay. The next question, I think this is gonna be really cool if you can do it. Then it's just kind of to kind of get something that subsume both KRV and OSVV. So here, right? This is like a log n cut expanding or one flow expanding. If you get log n flow expanding, it's just gonna subsume both of this. Okay. And the last question is faster. Anything faster? Oh. Faster than the running time of what we learned. This is the fastest cut matching game. And basically, currently, like all fast algorithm based on expander that we're gonna learn is based on cut matching game. But as long as you use cut matching game, you pay this much, log to the fourth. Like, can we hope for something like n log n, like sorting, that looks like a nicer bound? Like everything based on cut expander pay this much, pay log to the fourth factor. Can we do better? This is the kind of the bottleneck for the whole technology. Yeah, can we improve this? Right. Any questions? Yeah.
How did we get like log to the fourth? Because if I remember, like there are like log squared iterations, right?
Yeah.
And each iteration is bounded by O of n.
No.
Shouldn't it be log?
Is each iteration in round I? You spend ni.
Yeah.
The reason is, like you kind of multiply a vector to I many matching. Like what you do is like you multiply this random vector to this pi minus 1. What's pi minus 1 is just m1 times m2 times m3 up to.
Okay. And I goes up to
Log square.
Right?
Right.
So it's okay.
So in each round it's like n times log square.
It's really like O of n times I squared, and then I goes to log n.
Exactly.
Okay.
Exactly. So the total time is to log square
Okay. Yeah.
ni. Yeah. Which is this thing. Yeah. Just some people might say that shaving log is like it's just shaving logs, but can we like? But this is kind of really at the core of like at the bottleneck of the whole technology. So shaving this log is motivated. Yeah. More questions?
I have a question about that. So you were saying like we need at least log n round to make it connected.
Yeah.
Doesn't that give a lower bound of log n? Like the number?
Yeah, it seems like that gives low bound of log n as long as you add one matching per round.
Oh. But isn't the current best like square root log n? So
Yeah, I'm now confused. Like why? Good point. Yeah, why this is non-trivial. So maybe my argument is wrong here.
I think you can choose 2 matchings from left and like 4 points from the right matching.
So my argument here is wrong.
I'm not super sure, but it's like actually like 2 matchings, two edges from the left and 4 nodes from different edges on the right.
Okay. Let's take this offline. But yeah, maybe this is not valid. This is just because otherwise this lower bound. Yeah, this is not easy lower bound, and this is too easy. So yeah. Okay. One more question. Okay. So yeah, anything like any of the questions that I listed so far, if you are interested, let me know. Yeah, it's a possible project to work on. All right, then see you on Thursday.